function. So now how can we have for the higher order of vector derivatives? It's just like if you have the regular function where you have the y equal to x cubed. So when you want to differentiate for the first order, so you have y prime or dy over dx, so you got 3x squared, and then the second order y prime, and then you prime again, which means that second order, so you differentiate again with respect to x, so you got 6x, and then y triple prime, and then you got 6. So the process of the vector function also the same, okay, but the difference is only you have to differentiate them for each component. Okay, so now we have an example 7. So now we want to work on this example. Okay, you're given single function, vector function f. Now we have to find the second order derivatives when the t is equal to 0 and the dot product between the f prime and f double prime. Okay. Okay, so now the vector function f in terms of t is given by e to the power of 2t, e minus 2t, and then t multiplied by e to the power of 2t. Okay, so for the first derivatives, we have to differentiate with respect to t, so 2e to t, then negative 2e minus 2t. Okay, and then for this term, you have to apply the product rule, where you have for this one, so u is t and v is e to t. So u prime, which is differential with respect to t, we got 1, and then v prime we have 2e to t. Okay, so now we apply the product rule, u v prime, so 2t e to t, 2t e to t, okay, plus vu prime, so e to t. Okay, so that is the f prime. Okay, so for the second derivative, second order of the derivative, we differentiate again all the component with respect to t. So we got 4e to t, 4e minus 2t, and here for this you need to apply the product rule again. Okay, so for that we have u is 2t and v is e to t, so u prime is 2, v prime is 2e to t. Okay, and then when we plug in, so u v prime, so you got 40 e to t, u v prime to 40, and then v u prime, so you got plus 2e to t. Okay, that is only for this one, and then differentiate this with respect to t, then we got plus 2e to t. Okay, then we need to simplify. So we obtain 4e to t, 4e minus 2t, 40e to t plus 4e to t. Okay, so because from the question you have to find so you have to find, just a second, oops, it's fine. Okay, you have to find the f double prime and t is equal to 0. Okay, so the question asking for f prime when t is equal to 0. So we got 4 and then 4 and 0 plus 4. So we've got 4, 4, 4. Okay, and then the second one, so f prime t multiplied by the second derivative. So you need to multiply this and this. We have the dot product. Okay, it's not just a regular multiplication, but in vector there is no regular multiplication between two vectors, whether you have dot or cross. Okay, so just now f prime, okay, f prime and f double prime. Okay, so f prime t, the dot product between f prime t and f double prime t. Okay, f prime t, so we look at the component. So you have this one and this one. Multiply. So you got, let me copy first, 2 e to t multiplied by 4 e to t. Okay. Okay. And remember the dot product, you don't have the vector form anymore. Okay. So now we go to the second part, which is the y multiplied. So minus 8 e minus 2t e minus 2t. Okay, and then for the third one belongs to z. So we have this one and we have that one. So you have to, okay, so that is the multiplication of the z component. It's a bit longer than the other component. Alright, so now it's time for us to expand. You need to expand this one, and of course this one. Okay, so then we need to expand. Thank you. Alright, okay, so when you expand that, so 8 so now you have e to t, so the power, and when they are multiply each other, you have to add. So 2t plus 2t, so we have e 2 plus 2 4, so got 4t. Okay, and minus 8 e minus 4t. Okay, and this one, so you have to be careful when you want to expand. So 4 to 8, 4 2 will give you 8t square e 4t plus 8t e 4t. Okay, now we have this one plus 4t e 4t plus 4 e 4t. Okay, so is there anything that we can simplify? So E40. Now we have for E40 just 40. Okay. So for that we have 12 E40 minus 40. No, there is no. So minus 8 E minus 40 this one and this one will give you 12t e 40. Sebentar. So plus 8t square e 40. Okay, so that is the outcome of the dot product between f prime and f double prime. So we give you a constant, an expression in terms of t, not a vector form. Okay, so next, okay, vector partial derivatives. Okay, when we are talking about partial derivatives, for the regular function, if you have, for example, z equal to x cubed y. Okay, now you have a function of the two variable function. So meaning that if you want to differentiate, you cannot differentiate respect to x and y simultaneously. So you have to differentiate partially. So that's why the word here is called as partial derivatives. So I think in math method 2, we have discussed on the partial derivatives for two multivariable function, isn't it? So the procedure is the same, but now we are applying the technique in vector function. Okay, so let's say z you want to differentiate partially with respect to x. So you have del z over del x, or in a more simpler version, you have z of x, zx. So what's the outcome or the answer? You just differentiate the x with respect to this one, the expression, there is only x, so the y is just fixed. Okay, so now we got 3x squared y. Okay, so now we want to look at the example in example 7a. So you are given the vector function in terms of u and v. Now you have to get the specific partial derivatives as stated there. Okay, so now we want to work on it. Okay, so now here you are given this vector function in terms of u and v. So first one, you have to differentiate f with respect to u, fu. Okay, so you differentiate that, meaning that each component you have to differentiate only with respect to u, where the v is constant. Okay, now look at your first component. You just look at the u. Okay, and differentiate u, you got 1, so you have only 4v. Okay, and for the second component, now you have two terms here. So the first term, your u is here and v constant, so you have u squared, you differentiate u squared, you got 2u, and there is v. Okay, and then the second term minus u, and u here, you differentiate u respect to u, so it's become 1, so minus 5. And then for exponential function, you have u in exponential function, so you just apply the chain rule, differentiate the outer function, which is e, you will get the similar u, v, and then multiply with the derivatives of the uv. You differentiate uv with respect to u, v constant, so you have only v. So that is your answer. Okay. And then we move to the second one, fv. So the second one, fv. Okay, so the first term, now we focus on the v. So this is your v. So you got 4u, and the first term here on the second term, on the second component, you have u squared minus, okay, 5u, there is no v, meaning that all these are constant. When you differentiate constant, you got 0. Okay, and then we go to the last component, differentiate E, you will get the E back, E UV dot, and just focus on the now your you want to differentiate respect to V. Your UV, when you differentiate respect to V becomes 1, so the on the left is U. So that is your FV. And then next, the second order. The second order from the FU and then U, meaning that you have to use the FU that you obtain up over here, and you differentiate this again with respect to U. So we just use this result and differentiate the first term here, the first component with respect to U, where the V constant, so these all are constant. I mean, this term is constant. So when you differentiate constant, you got 0. Now this one. So we want to differentiate respect to U. So we got 2V minus 5. So 5 becomes 0. Okay, now you have VUV. Okay, since you want to differentiate respect to U, so V here is constant. So you can just have V there. You don't need to apply the product rule because V constant. So you differentiate the E, you will get the E back, UV, and differentiate the UV. Differentiate the UV here. Now you with respect to U. So you got V. So when you simplify, you got 0, 2V, V squared, E, UV. Okay, so that is second order. And then the mixed partial derivatives. Mixed partial. So if you look at there, you have FUV. What does that mean? So F, U, and then V. That's mean you find out the FU first, you got the value, and then after that you differentiate with respect to V. So again, we are using the result of the first question, FU, here, and we differentiate this with respect to V now. Okay, so the first term, your first term, there is V. So when you differentiate FU with respect to V, then you got 4. Okay, now look at the second component. What is your V? Now that is your V. So when you differentiate respect to V, so 2UV becomes 2U. 2U and 50. And this one, what is your V? So you got 2V here, outside the exponent and inside the exponent, meaning that this is multiplication of two functions, so you have to apply the product rule. Okay, so you have to be careful there, meaning that, so now you have E UV dot V. So your differentiate the, so I'm not using the UV again, it's a bit confusing, so just assuming we take this and differentiate this with respect to V, so it's become 1. So E UV in 1 plus V E UV dot U, because you differentiate respect to V, right? So you differentiate respect to V here, so you got U. So that's why this is chain rule, okay? The combination of the chain rule and product rule. So now we simplify. 4 2U E UV plus UV E UV. So that is your mixed partial derivatives of FUV. FUV, FVU, the outcome will be the same. Why? As we discussed in on method 2, if you have a mixed partial derivative for second order, if you have the regular function f, xy, and the expression or the value is always the same of the fyx, we just change the order. Okay. maybe you can check. How about if now we, okay, let's say now we want to check. How about if we have f v and then u, which means that by using the result of fv and then we differentiate with respect to u. So where is fv? So this one, by using this and we differentiate with respect to u. So you got 4. Okay, just look at here. Now you have here v, this one. Okay, differentiate for u with respect to u. You got 4, so you got 2u, and then this one you have, okay, again you have e u v, and then I put u here, u e u v, and you have to differentiate. You have to differentiate del that component with respect to u, del u of this. You need to apply the product rule because you have the u inside the exponent and outside the exponent. So you have to apply the product rule. So u is u and differentiate euv with respect to u. So you got v e uv plus e uv1. So now you will get e uv plus uv e uv. You did the same. So you also compare the fuv and fvu. So you got 4, you got 2u, and this one you have euv plus uv euv. So we got the same. So we can say that fuv is equal to fvu. So this result is actually the same as for the the general, the regular function. Okay, so for second order of mixed partial derivatives, so the value of them and all the expression will be the same. Okay, so okay, what else? Okay, so the second order of fvv. Okay, now we have fvv. Also meaning that we have to use the fv and then we differentiate again with respect to v. Okay, where is fv? fv, again we use this one. Okay, you need to use that and differentiate with respect to v. So the first term you got 0. Why? Because there is no v there. So when you differentiate with respect to v, so this one 0 and this part also 0. Okay, so the second component also 0, and the third component, okay, look at here. Since you want to differentiate this term with respect to v, but the v is only in the exponential function, so you don't need to apply the product rule. So u is just a constant. So u is u. So e uv multiplied by u. So you obtain that you got the second order with respect to v, 0, 0, u square e u v. Okay, so if I did something wrong, so please let me know so that I can correct it. Okay.